Welcome to the deep dive. Today, well, we're cutting through all the noise.
Right.
We want to bring you something really mind-bending. A breakthrough in physics.
It sounds like science fiction, honestly.
Doesn't it? But it's very real. It could totally redefine how we store data, maybe even how our computers, think. We're diving into a recent SciTech Daily article looking at some really groundbreaking work. It's from the Universitat Autònoma de Barcelona and their collaborators.
A strong team.
Yeah. So our mission today is to really unpack this. What is this discovery? Why is it such a game changer for tech? And, how could it fundamentally transform computing?
And what I find truly compelling here is seeing how that fundamental physics, the really deep stuff, connects directly to, well, real-world impact.
Exactly.
We're talking about something that doesn't just push knowledge forward, but really opens the door to massively more energy-efficient devices.
Which we desperately need.
We do.
Yeah.
And maybe even more remarkably, it could lead to tech inspired directly by, the human brain.
Okay, so let's start right there. This Vortion. Can you define that for us? What exactly is it we're dealing with?
Okay. So at its core, a Vortion is basically a brand new magnetic state. Technically, a magneto-ionic vortex.
Magneto-ionic vortex.
Yeah, and they actually created it experimentally. They did it by precisely manipulating ions.
Ions.
Yes, using voltage, and all at the nanoscale, so super tiny.
Wow.
Visually, you could maybe think of it as a tiny whirlpool, a sort of magnetic pattern, like a microscopic eddy.
Okay, a tiny magnetic whirlpool. That's a good visual. But let's connect that microscopic thing to the bigger picture. Why is discovering this tiny whirlpool such a huge deal for, say, information technology?
Well, right. If you look at the big picture, IT, the explosion of big data, we have a major problem.
Energy consumption.
Exactly. Data storage today, it mostly relies on electric currents. And that process generates a lot of excess heat. It just wastes tremendous amounts of energy.
We all feel our laptops getting hot.
Precisely.
Yeah.
So this discovery, it offers a fundamentally more efficient alternative. Controlling magnetic memory with voltage instead of current.
Okay, voltage, not current.
That's the key. And these magneto-ionic materials are crucial because their magnetic properties, you can actually adjust them just by inserting or removing ions. And you do that by changing the voltage polarity. So it's a much cleaner, a much more efficient way to store information.
Now, I feel like we've heard about magnetic vortices before, though. What's the key difference here? What makes these Vortions, as they call them, a real breakthrough?
That's a really important distinction, yeah. So previous work in magneto-ionics, it mainly looked at continuous films.
Okay.
Which aren't really practical for the sort of nanoscale bits you absolutely need for dense data storage.
Right, you need tiny individual units.
Exactly. And while, yes, magnetic vortices existed, they were incredibly difficult to modify, or it took significant energy to change them. So the Vortion, it cleverly combines the magneto-ionics and the magnetic vortices. It offers this on-demand control of what they call nanodots.
Nanodots, so like tiny magnetic pixels.
That's a good way to think about it. Incredibly tiny, billionths of a meter across. Each one could hold a bit of information.
And the energy saving comes from?
It comes from how they achieve it. They extract nitrogen ions using voltage. And crucially, that leads to very, very low energy consumption.
Right.
Irina Spasievich, one of the researchers, she really highlighted this. Using voltage instead of current, that's the breakthrough.
Okay.
Because that voltage procedure, it basically prevents the heating in devices, laptops, servers, data centers.
There's huge implications there.
Huge. It drastically cuts down energy loss. And Jordi Sort, another researcher, he emphasized that this is, and I quote, a so far unexplored object at the nanoscale. He also noted these very interesting dynamically evolving spin configurations.
Spin configurations,
Yeah.
so how the little internal magnets are behaving.
Exactly. How they're arranged, how they interact. That directly controls the material's magnetic properties and behavior. It's really unique to these nanostructures.
Okay, the level of control you're describing, it just sounds unprecedented. What does this actually let them do? What can they control?
Yeah, the control is pretty remarkable. Researchers can now basically vary the material's magnetic state almost at will.
So switch it on and off.
More than that. They can switch it from non-magnetic to having a uniform magnetic orientation like a normal magnet.
Okay.
Or to this new magneto-ionic vortex state. And they do this just by precisely controlling the thickness of the magnetic layer they generate with the voltage.
Wow, just by voltage duration.
Well, duration affects the thickness, yeah. And it's not just the state. They can actually tune the fundamental magnetic properties.
Like what?
Things like how strong the magnetic signal is, that's magnetization, how resistant it is to outside magnetic fields, coercivity, how well it remembers the information, remnants, also anisotropy, which is how properties change with direction, and the critical fields needed to flip its state.
So real fine-tuning.
Exactly. Spasievich put it really well. She said with these vorations, they have, quote, unprecedented control of these properties.
The fundamental ones for memory.
The absolute fundamentals for storing info in magnetic memories. And importantly, they can control and tune them in an analog way.
Analog, not just on-off.
Right. And reversibly. All activated by voltage with very low energy use. The properties actually vary depending on how long you apply the voltage. So it allows this incredibly fine-tuned analog and reversible manipulation.
That level of control at room temperature, you said, and nanoscale, that's really astonishing.
It really is.
But the part that really jumped out at me reading about this was the connection they made to the human brain. How on earth can these vorations mimic neuronal synapses?
Yeah, that's where it gets even more fascinating, right? It raises this huge question about how we could use this discovery for completely new ways of computing.
Like neuromorphic computing.
Exactly. These vortations, they can provide tunable neuronal synaptic weights.
Synaptic weights, like the strength of connections between neurons.
Precisely.
Yeah.
It mimics how those connections in our brains adapt dynamically, based on activity learning. Jordi Sort actually envisioned, and again I'm quoting, the integration of reconfigurable magneto-ionic vortices in neural networks as dynamic synapses, capable of mimicking the behavior of biological synapses.
So the vortations could act like the brain's adjustable connections.
That's the idea. And the parallel is quite striking when you think about it. Biological neurons and synapses, they're also controlled by electrical signals and, crucially, ion migration.
Ions again?
Ions again. Just like these magneto-ionic units operate with voltage and moving ions. It's a surprisingly close analogy at that fundamental level.
It's just wild to think about our laptops basically being miniature heaters, like you said, and this could fundamentally change that equation.
Absolutely.
What kind of energy savings are we realistically talking about, globally if this tech really took off?
Oh, the potential savings are just monumental, especially if you think about data centers. They are massive energy consumers right now. This could make a huge dent.
Okay, so energy saving is huge. Brain-inspired computing. That's mind-blowing. What other potential real-world uses do the researchers see for these new magnetic states?
Well, beyond those two big ones, the list is pretty broad, actually. They see possibilities in analog computing.
Analog?
Yeah, computing that's not just binary, not just zeros and ones. Also, multi-state data storage systems. Again, storing more information than just a 0 or 1 in each bit.
More density.
Exactly. And even specific medical therapy techniques. They mentioned theragnostics.
Theragnostics.
Yeah, it's a field combining therapy and diagnostics. Also potential impacts on data security and something called magnetic spin computing devices.
Spin logics.
Spin logics, right. Using electron spin instead of charge for computation. And generating spin waves, a field called magnonics.
Magnonics, okay.
Which could lead to totally new ways of processing information without even moving electrons around.
Yeah.
So yeah, a really wide range of possibilities.
It sounds like a foundational discovery.
It really does. And it's worth remembering, this wasn't just one lab. It was a big collaborative effort.
Right, you mentioned Barcelona.
UAB, yes, but also ICM, CSC, the LBA synchrotron here in Spain, and collaborators from Italy and the United States too.
Yeah.
It really took a combined effort, and their findings were published in Nature Communications.
A top journal. So, okay, let's try and wrap this up for you, the listener. We've just explored something truly groundbreaking, scientifically speaking. The vortation. This new magnetic state, it offers this unprecedented low-energy control over magnetism right down at the nanoscale.
Yeah.
And that promises to revolutionize everything from how we store our data to maybe even how we design the computers themselves.
And I think the key thing is this isn't just some, fascinating lab curiosity. It really feels like a significant leap, a leap towards technologies that are far more energy efficient, much more adaptable.
And potentially blurring lines.
Potentially blurring the lines, yeah, between our traditional electronics and the incredible complexity of, biological brains. It really could pave the way for a whole new era of computing.
So here's a thought to leave you with. Just imagine a future where your devices don't just compute, but they learn and adapt almost like a biological brain.
Powered by these tiny magnetic whirlpools.
Exactly. All powered by microscopic magnetic whirlpools, saving incredible amounts of energy in the process. What does that kind of fundamental control over matter really mean for our world in, say, the next decade?
It's a profound question.
Something to think about. Thank you for joining us on this deep dive.